Gradient descent is a method used in machine learning, data science, and mathematics to help computers learn. It is one of the core techniques behind training models such as neural networks, recommendation systems, and many predictive algorithms. The goal of gradient descent is to find the best set of parameters that make a model perform as accurately as possible. To understand why this method is needed, consider that many models require adjusting thousands or even millions of internal values. These values determine how the model behaves. If they are set incorrectly, the model performs poorly. The challenge is figuring out how to adjust these values to make the model do a better job. Gradient descent is the strategy for doing that. Whenever a model makes a prediction, we can calculate how far the prediction is from the correct answer. The difference is called error or loss. The entire goal of training a model is to reduce this error over time. But imagine trying to reduce error when there are many values influencing it. You cannot simply guess. You need a systematic approach. Gradient descent provides that approach by treating the error like a landscape. The model is standing somewhere on that landscape, and it wants to move to the lowest possible point, the place where the error is the smallest. Think of the error landscape as a mountain range. Each point on the ground represents a possible setting of the model's parameters. The height at each point represents the amount of error. High altitude equals high error, a bad solution. Low altitude equals low error, a good solution. The goal of gradient descent is to walk downhill until we reach the lowest valley. But there's a catch. The landscape is huge and full of twists, hills, dips, and valleys. You cannot see the whole thing at once. You only know what the ground looks like right where you are standing. So how do you move? You look at the direction the ground slopes downward and take a small step in that direction. Then you repeat. This is exactly what gradient descent does. The process begins with an initial guess for the model's parameters. Using current parameters, the model makes predictions, and we measure how wrong those predictions are. At this point in the error landscape, we check which direction error increases and which direction it decreases. This direction is derived from the gradient, essentially the steepness of the slope. We take a small step in the direction that reduces error. The process loops: calculate error, find slope, step downward, repeat. Over many repetitions, the model gradually works its way toward a minimum error. If you take steps that are too large, you may overshoot and miss the lowest point entirely. If you take steps that are too small, training becomes slow and inefficient. So gradient descent has a setting that controls step size. This is known as the learning rate. Picking a good learning rate is important. Too high, unstable learning. Too low, slow learning. Just right, efficient progress. Because the error landscape can be complicated, it may have multiple valleys. Some are shallow, some deep. Ideally, we want the deepest valley, the absolute lowest error. However, gradient descent only sees the ground locally. It does not know whether the valley it's descending into is the deepest one. Sometimes it settles in a smaller valley when a much larger valley exists elsewhere. This is called getting stuck in a local minimum. Advanced variations of gradient descent include techniques that help escape these shallow valleys and find deeper ones, improving model quality. Every weight inside a neural network is a parameter. Gradient descent adjusts these parameters to improve prediction accuracy. Models that predict trends, values, or relationships use gradient descent to fine-tune their coefficients. Platforms like Netflix or Spotify use gradient descent to adjust internal models based on what users like or skip. Modern AI models that understand text, generate images, or classify objects depend heavily on gradient descent during training. Robotic systems use gradient descent to improve motion planning, stability, and decision-making. Gradient descent is literally one of the engines of modern artificial intelligence. Advantages: simple and intuitive, scalable, flexible. Limitations: can get stuck in less than optimal solutions. Sensitivity to learning rate choice may require many iterations for complex models. Despite these limitations, it remains the central technique used to train AI systems today. Gradient descent is a method for improving a model by gradually reducing its prediction error. It does this by viewing the error as a height landscape and moving step by step downhill toward the lowest possible point, the point of best performance. It is easy to understand conceptually, yet powerful enough to support the training of today's most advanced artificial intelligence systems. In short, gradient descent is how machines learn from mistakes, one step at a time.